Hello, welcome back to Organic Chemistry 2330. I'm David Irvin, and we'll be talking today about finishing up our chapter on alcohols and starting our next chapter. I have had time to finally do all grades for the chapters 1 through 7, as well as the exam. The exam grade on Canvas is the curved grade. The raw average for the exam was 67, which is not bad. Actually, I found that very good. And the curved average is 75. So that's my current target for trying to get the class average somewhere around 75, get good differentiation between A's and B's, but I don't lose as many people to DWFs if I keep that average that high. So that's my current goal there. All right, any questions before we begin? Okay, I have the chat open. If somebody could ping the chat, just to make sure it's working.
Sorry, did you say that on Canvas it's already curved?
If you update right now, it should be the already curved one. Yes.
Okay.
I just did it.
And then for okay, thank you. And for chapter 9 on your file video notes, there's one that says RXN. Do you know, is it both or which one?
RXN is just the reactions. The other one is all of the slides.
Okay, thank you.
So I did that because some people wanted to review just the reactions, and that's what that is.
Okay, cool, thank you.
Okay. So what we're going to do is we're going to continue on with chapter 8. So we have a little bit more to talk about epoxies, and then we're going to talk about thiols as well. I have a question in the chat that says, does Zaitsev rule only apply to alkenes? And it will not. Yes, that is true. Zaitsev's rule only applies to alkenes because you only have one group on each carbon anyway for an alkyne. So where the parts that you're removing on the alkyne shows you where the alkyne is going to be, whether it's going to be at the end or in the middle. The alkenes have an opportunity to do one or the other. So in the alkenes, always look for the more substituted alkene. That means it's going to be more stable. Therefore, we are following Zaitsev's rule. Okay, does that answer your question? All right. Okay, so let me go ahead and start sharing my screen. I don't want to do that. I want to do that. Okay, I'm going to move my peanut gallery up over here. So there's only 21 of us, so I can see us all. Hey, there we go. Okay, and I have to move this over just a little bit. Can you still see the slides? Sometimes it disappears.
Yes, we can still see them.
Okay, great. Okay, so we talked about a special kind of ether. So in this chapter, we talked about alcohols and the fact that they hydrogen bond, and that controls a lot of their properties. We talked about what we can do with them. We can oxidize primary alcohols. We can substitute the OH group off there. We can lose water and make alkenes, right? So those are the kind of reactions we can do with alcohols. But ethers tend to be much less reactive unless we have this three-membered ring called the epoxy. And the three-membered ring is driven by an attack by a nucleophile to open that ring and give us a variety of products. If we're attacking with a hydroxide, we're going to end up getting a diol. But if we attack with other groups, we will end up getting other functional groups, but they will always have an alcohol in them, because the oxygen from that ring will open up, giving us an alkoxide first, the negative charge first, and then something there will give it a proton, and you'll end up with an alcohol. So we can get this amino alcohol, a diol, or a thioalcohol. So all we have to do is attack it with any nucleophile, which is anything with a lone pair or a negative charge. We're going to open that ring and generate a new functional group. Okay, let me go ahead and mute my watch since I'm getting so much email. Okay, so that's the joy of epoxies. But wait, if we can ring open to generate that alcohol, we can use this as a way to control the structure of our materials. And so, for example, if we wanted to build these pharmaceutical drugs, starting with the epoxy, we could do that by taking our epoxy, attacking it with our amine to ring open it, giving us that alcohol, and then react that alcohol somewhere else to give us our other compound. And so things like Novocaine, which is a topical anesthetic, or Benadryl, which is actually I use as a sleep aid, but also does a great job at clearing out. I think it's not an antihistamine; it's decongestant. So, but they all contain that, and so somewhere in the synthesis of this, they took an epoxy, attacked it with an amine, and then that gave them the alcohol they could use on the next step of the reaction. Okay, so questions about that ring opening reaction with the epoxies. All right, so that is probably the only reaction we have with an ether, but it's only going to be that 3-membered ring. Okay. So we talked about alcohols and they hydrogen bonded. We talked about these ethers, which don't have a hydrogen-hydrogen bond. Now let's talk about the analogous system with a sulfur, and they're called thiols. Okay, so a thiol is just like the alcohol, except instead of oxygen, you have sulfur. Sulfur is one more row down. It's a group 3 element, so it's bigger. Okay, it is has a lower nucleophilicity than the oxygen does, but it's larger, so it can more easily stabilize charge. So that makes that hydrogen a little more acidic than it was for the alcohol. However, even though it's more acidic, the bond, the nucleophilicity difference between the sulfur and the hydrogen make it less reactive toward hydrogen bonding. Okay. Now, again, sulfur is big and large, and it has 2 large lone pair groups on there. So it's spinning us a little bit out of that 109 degree, even though it's sp3 hybridized, a little bit closer to around 100, that those 2 lone pairs take up a lot of space. Okay. So let's talk about naming them first. So if it's the only thing on the chain, this is a low priority group, it's less than amines and it's less than alcohol, so it has to be the only thing on the chain, you can actually just call the parent chain what it is and add the word thiol to the end. Thiol is the sulfur one. Okay, so that means if we have a chain of 2 carbons, we'll call that ethane thiol. If we have a chain of 20 carbons, it'd be icosane thiol. Okay, so it's just easy to do that. If there's any other group on there other than a halogen or a benzene ring, you're going to make it a substituent. And when you have it as a substituent, you're going to name it for the compound called the mercaptan. Okay, so if you have any other group on there, you can name it mercapto in the system. So in the case of this right here, alcohol is higher priority than the thiol, so the thiol is now a substituent. So now we have ethanol, because we have 2 carbons and the alcohol, so we have ethanol. But we also now, this is our number 1 carbon, this is our number 2 carbon, because we're naming it for the alcohol. We have 2 mercapto ethanol. This is used a lot in biological biochemistry kind of work because it works as a great reducing agent. It takes other things and it denatures proteins as well. So it's the parent chain plus thiol if it's one of the only groups there. If it's a substituent, it's mercapto. Okay.
I have a question about the functional groups really quick. Like as a whole, is there a list that puts them in order of their priority?
Oh, that's a great question. Yes, there is. On Canvas, there is the nomenclature review on that. Not only does it have all the different rules, but it has on the last page a priority list. Okay.
Great, thank you.
So it is on, it's a great resource to try to name things with. And you'll see that on the bottom is things like nitro groups and chlorides and those things that don't change the name. Okay. Then we start changing the name with amines, then thiols, and then alcohols. And then it gets more and more complex as we go up to from there. Okay.
Thank you.
So one of the biggest physical properties that these thiol compounds have is stench. They stink really bad. Okay. Now, we can use that to our advantage because you can sense that at very low concentrations. Turns out you can sense most thiol compounds in the part per billion range. And that's just with your nose. We're not even using scientific equipment here, okay? So we're using that in our advantage because natural gas and propane actually has zero odor. There is no functional group there for us to sense. So we wouldn't know when something like that was building up, okay? So what they do is they put a volatile mercaptan in that gaseous stream, so it comes out with the natural gas. And since we can smell it in parts per billion, we smell that smell before we get a high enough concentration of gas to be explosive. So it's a great safety thing, the fact that our noses are so sensitive to these. Now, this is also a same thing that's found in skunk and found in baby poop and rotting cabbage. Those all have certain amounts of thiols coming out of them when they are there. So this is a very useful function, but it's also very bad function. Story. I used thiols in my first 2 years of graduate work, and I had to bleach my hands before they came out of the hood, or I would drive everybody out of the room. Okay, it was that bad. My hands would have to be bleached, converting that thiol into a sulfonic acid, and then that becomes non-volatile. So my hands were horribly stinky for the first 2 years of graduate school. Then I went on to another project and I didn't have to do it again. But anyway, so let's talk about the physical properties of thiols. Thiols, because the sulfur and the hydrogen are pretty close together on their electronegativity, they actually have a pretty nonpolar bond. It's about the same polarity as a carbon-hydrogen bond, okay? What that means is it doesn't contribute to hydrogen bonding very well at all. The bond is too nice and stable, it's too nonpolar, and therefore it contributes to hydrogen bonding less than the oxygen analog would be. So if we look at this, where we have the similar molecular weights, we have methane thiol and methanol. Because it's not hydrogen bonding, it's like 60 degrees lower in boiling point, okay? And that's all an effect of the hydrogen bonding, okay? With the ethane thiol versus the ethanol, again, it's about a 43-degree difference between them, okay? And when we get up to the butane, now we're starting to see a little more van der Waals forces in there, and they're getting a little bit closer together. They're only about 19 degrees apart. So what does that tell us? That tells us that hydrogen bonding plays a bigger role in alcohols than it does for thiols, okay? And it's all about that bond polarity. So technically they do hydrogen bond a little bit, but if you're looking on a scale of hydrogen bonding, alcohols are higher hydrogen bonders than nitrogen, which are higher hydrogen bonders than sulfur. And the strongest hydrogen bonder is between the hydrogen and fluorine. Okay. Okay, so just like, oops, I'm trying to get rid of that alert here. Just like alcohols, that hydrogen is acidic, and so, but because the sulfur is so much bigger and can stabilize that negative charge, thiols are more acidic than alcohols, okay? Now, it goes to those trends of what makes something more acidic. Is it a more stable anion? Is it a bigger anion? Is it more electronegative? Does it have an inductive effect? In this case, it's the size of the anion formed. The sulfur anion is twice as large as the oxygen anion. Therefore, it's more acidic, okay? Doesn't hydrogen bond as strong, and it's more acidic, okay? So if it's more acidic, if we were to take that proton off and turn it into a base, it is going to be a weaker base than, it's going to be if it's a strong acid, it's a weak base, right? Which means that the alcohol is going to produce a stronger base than you can produce with the thiols. So when you react a thiol with something like sodium hydroxide, it's going to create the thiol salt, which will be less basic than the hydroxide. Okay. Questions on hydrogen bonding and or acidity of thiols? Okay, So there's also a couple other things we can do with thiols. And the fact is that they are used a lot in biological systems, specifically in proteins, okay? Proteins are long chains of amino acids that are held together in certain configurations, so they have reactive slots that are specific to different chemicals, right? Now, the thing that holds them in place is what we call the disulfide bond. What that is when you have a thiol next to another thiol, you're going to oxidize these such that they lose the hydrogen and you get a sulfur-sulfur bond. That's a disulfide bond. Two sulfurs, disulfide bond, okay? So this happens very readily in the air. And so that's one way we can do it with proteins. It holds them in place. The other thing is it's also used in straightening or curling hair. Your hair has a variety of proteins in it, and it uses dithiols in there. That's why you tend to have a two-part system where you do a reducer, and then you form it into whatever size you want, either straight or curly, and then you have a fixer, and that reoxidizes those dithiols to disulfides to get it to fix in that new position. The other cool chemistry that thiols do is that it also is used in tires. They create these disulfide bonds in tires, and it's called vulcanization. It takes a rubbery, soft material and turns it into that very durable rubber material we see in vulcanized tires. So that's the same chemistry we're using. We're using those disulfide bonds in between alkenes in the rubber to make that reaction happen. So sulfur is very important, although it is very sneaky. Okay, so let's look at this right here. We have lipoic acid is a growth factor for bacteria and protozoa, or single-celled organism, and is essential for several enzymes in the human body. Okay, so let's talk about what functional groups we have just in this compound here. Lipoic acid. Acid is spelled wrong here, sorry. Okay, so what functional groups do we have? There's only 22 of us, come on, we can talk.
Carboxyl group.
Okay, we have a carboxylic acid, and what other group do we have?
We have a disulfide bond.
We have a disulfide bond. So one interesting thing that might happen in this as it's being processed for the body is this disulfide bond can be reduced. So you are having something else in your body oxidized to break that disulfide bond apart. And then that new dithiol can move around somewhere else, and it can be oxidized by some other chemical reaction back to the disulfide. So going from the disulfide to the dithiol to the disulfide allows you to do oxidation and reduction reactions within the bloodstream and within the cells of the human body, or all, biological systems. So that's kind of the interesting thing about it. It's easy to oxidize, it's easy to reduce, and it happens right at the pH of our blood, which is about 7.8. Okay, so that is alcohols, ethers, and thiols. Okay, so questions on that right there.
How do you draw the structural formula for the previous question? Like
sorry, how do you draw? Oh, the reduced form. Oh, okay, yeah. So the idea is we're going to be breaking this bond, and so what we'll end up with is SH over here, SH. One more carbon, COOH. So we end up with this dithiol, and it's a 1, 2, 3. But of course, if we're going to name this IUPAC-wise, we have to go with the idea that we're going to have to start from the carboxylic acid over here. This is 1, 2, 3, 4, 5, 6, 7, 8. So this would be 6,8 dimercapto octanoic acid.
So those hydrogens that come from the cycle structure.
When you reduce that disulfide bond, you'll end up creating two sulfurs with negative charges on them, and then they'll be acidified by something in the solution. And so you'll get the hydrogens from like water or whatever else is in the solution. Does that make sense?
Yeah, I figured it was from like the solution or something.
It's not SH2 because our sulfur here is sp3 hybridized and has 2 lone pairs. So it's just SH. Okay. SH2 is actually a very toxic gas that binds, that is really bad for lungs and stuff. Okay. And it's called hydrogen sulfide. Okay, so that's thiols, oxygens, and ethers. Obviously, focus on the reactions of the the oxygens, because there are many more reactions for the oxygens than there were for the ethers and the thiols. Remember, the thiols and ethers only have about one reaction we really care about, which is that disulfide bond and the ring opening of the epoxy. All the other reactions in this chapter are related to the alcohols. Okay. So that being said, it's time to move to chapter 9. Okay. Chapter 9 is a whole new thing. We're going to talk about benzene and its derivatives. Okay, so at the beginning of the chapter, at the beginning of the class, we talked about how we had hydrocarbons and different classes of hydrocarbons. And so we had alkanes, alkenes, and alkynes. And we've done a lot of naming and stuff with that, okay? But then the other kind of hydrocarbon we had was what we called an aromatic hydrocarbon. And that's where benzene comes in, okay? So in the case of benzene, they were early in the days, they didn't have all the fancy instrumentation we have, but they could figure out how many carbons or hydrogens they had on them by combustion. And what they found was that they figured out that benzene had 6 carbons and 6 hydrogens, and it did not react like other things, okay? So it was very different, okay? So when they first drew the Lewis dot structure, before they even knew what Lewis dot structures were, of the structure of benzene, they said, okay, 6 carbons, 6 hydrogens. How do I do this? Oh, it must be in a ring and it must have 3 double bonds in this 6-membered ring, okay? But just like we talked about with resonance structures, this isn't the only way to draw it. We can actually have the double bonds flip over into this other section. And so we end up having this kind of structure here, okay? So in Kekulé's mind, it could be either one of these resonance structures or somewhere in between. However, that would mean that this would react like it has alkenes in it, and it doesn't react like it has alkenes in it. Alkenes react completely differently than benzene. So there had to be something else going on here, okay? So what else was going on here was the fact that we had changed something about the system. We still have sp2 hybridized carbons, and we still have an MVP orbital making those double bonds, but it's not localized. It's not fixed in one space like we have with alkenes, okay? So if we think about that and how what an sp2 hybridized carbon would look like, it's going to be trigonal planar, right? So it's going to be flat. The p orbital is going to be above and below that plane, and all the bonds are about 120 degrees apart. Okay. Now, if this was alternating single bond, double bond, single bond, double bond, single bond, we would see a difference in bond lengths between this bond and that bond, but we don't. It's kind of the average of the two. So what seems to be happening is that we seem to be sharing those double bonds around all these carbons equally, okay? So when we're sharing our pi electrons over a number of atoms equally, we call this resonance or aromatization. But there's some rules. You have to follow 4 simple rules to have something be aromatic. Okay. So the first thing we have to think about is that, okay, we don't have a double bond, single bond, double bond, single bond, and they're not just flipping back and forth really fast, because when we analyze the compound, it doesn't react like it's double bonds, and it doesn't have alternating things. So they must be shared equally. So what does that look like? Well, we have our sp3 hybridized carbons making our ring here, right here. And so that leaves a p orbital on each and every atom in that ring. Okay? So instead of having a fixed double bond here and a fixed double bond here, fixed double bond here, what it does is it creates a toroid, or a ring of electron density that's equal all the way around the top. And it creates a ring of electron density that's equal all the way along the bottom. So if you can imagine, you have this flat set of carbons and a pillow of electrons on top and a pillow of electrons on bottom, and it's hard to tell which are being shared where. Okay. So what that tells us is that we have a continuous pi cloud going over all 6 atoms. Okay. So they're not fixed in any one space. That's the key to being aromatic. That's the key to this hybridization we have, is that they're not localized, they're shared over the entire system. Okay, so when Kekulé drew it, he drew it as these 2 alternating contributing structures, right? But it can't do that. These are contributing structures here, but it is definitely a hybrid between the 2 of them. It's not either one, it's never either one, because it doesn't react like a double bond. So it has to be somewhere in between. Okay. And so what we do when we try to draw that is we show that it's not in this structure or that structure. A lot of times when you see benzene rings, you'll actually have a ring in the middle of it. So that ring in the middle of a cyclohexane is telling you that it's shared among all of those carbons equally. I have a hand raised.
Have you gone over what a Kekulé structure is?
Well, Kekulé is just the guy who was trying to figure out why benzene reacted differently. And this is really technically a Lewis dot structure for us. We're going to use that Lewis dot structure. Kekulé is just the guy who tried to figure out why benzene was different. And so it's his theory on it. What he said was it was this, but it's not that. We found out later that it's not this equivalent contributing structures. Okay.
Okay, thank you.
All right. Still have your hand raised?
Oh no, I just had to put it down.
All right. So that brought about the idea that it couldn't be either one of those. It had to be some hybrid. Okay. And so that brings us to the concept of resonance. Okay. A resonance hybrid is a stable hypothetical contribution of the electrons in a localized structure. Okay. So basically, a resonance structure is the average of them, but the difference between, is what we call resonance. Okay. And there's an energy associated with this. The difference in energy between the resonance hybrid and the Kekulé structure. So the difference in energy between this structure here, which is our resonance hybrid, because we're showing it spread out over the entire system, versus the isolated in single and double bonds, is what we call resonance energy. So in theory, this is higher energy than this, because this is alternating single and double bonds. Here we have a shared set of bonds with a lower energy, and that sharing of that saving of energy gives it its stability. Okay, so it's going to save energy to be in this resonance structure or be an aromatic structure. Okay, and the way we can look at that is, let's look at the heat of hydrogenation, or the amount of heat it takes to add hydrogen to benzene, to prove to ourselves it's more stable. Okay, so if we just had one alkene in a cyclohexane ring, okay, so we have a cyclohexene and we added hydrogen across that double bond, okay, it's one of the few reactions that we can do with that hydrogen there, we would actually liberate about 120 kilojoules per mole of heat during that reaction. So that's the heat of hydrogenation, okay? So if we take it and in theory, we added 2 more of these, so it'd be a total of 3 of these, that should be 360 kilojoules, because if one is 120, the next one will be 240, the next one will be 360. So in theory, benzene should have a heat of hydrogenation of 360 kilojoules per mole. But when we hydrogenate benzene, it actually is only releasing 209 kilojoules per mole. Okay, so we're releasing less energy, meaning that it was more stable by the difference in these two numbers right here. It's more stable by that difference than just 3 double bonds in a cyclohexane ring would have been. Okay, so what does that look like? Okay, so theoretically, we have our cyclohexene here, and it was 120 kilojoules per mole. Our hypothetical, which is calculated from 3 of these in cyclohexane, should have been 360 kilojoules per mole. Okay. Now, cyclohexane by itself is at this lowest one here. We'll call that our baseline, what we're starting from. And all of these compounds, when hydrogenated, go to cyclohexane. So that's why we want to see the energy difference between the cyclohexane and the compound. When we actually do the reduction of benzene, it only releases it only releases 209 kilojoules of heat. What that means is that in theory, it should be this higher number, but the difference between the calculated and the measured is this 151 kilojoules per mole, okay? That's the energy that is the resonance has given us to make it more stable. It is 151 kilojoules per mole more stable as that resonance structure than as the theoretical trialkene, the triene of cyclohexane. So there's an energy savings, and that's why these aromatic compounds are aromatic, because they're saving energy. Okay. All right, questions on that. So having this resonance hybrid structure saves energy. So, and that resonance hybrid structure works for any set of rings as long as you can spread the charge out over those rings. So there's about 150 for benzene. There's about 255 for this 2 benzenes fused together called naphthalene. 3 benzenes fused together, it's called anthracene. And that's about 347. So any set of rings where the electrons can be shared equally over those rings has a savings in energy from being isolated double bonds. So there have to be some rules associated with this, right? So the idea here is that, okay, so there's some hybrid structure here, okay? And that hybrid structure saves energy. But not all compounds with double bonds in them have that saved energy. So there have to be some rules that say this does create an aromatic compound or this doesn't create an aromatic compound. So for something to be aromatic, Ulrich Kekulé came up with the idea that we have rules. The first rule is that you must have a ring, okay? So you have a ring. So you can have a ring of 4, 5, 6, 7, 8, 9 carbons, but there has to be 1 p orbital on each atom of the ring, which means all the atoms in the ring have to be sp2 hybridized and have 1 p orbital available, okay? The ring has to be planar or nearly planar. That's so that all the p orbitals can line up and give a continuous or nearly continuous loop around that ring. And you must have a certain number of electrons. You must have 2, 6, 10, 14, or 18 electrons. Now there's a formula for that that is, let's see, 2n plus 2, okay? N is just integers like 1, 2, 3, 4, 0, 1, 2, 3, 4, 5. So if it's 0, it's 2. If it's 1, it is 2, If it's 2, it's 4, it's 6. Oh, 4 plus 2n. Yeah, sorry, it's 4 plus 2n. So if it's 1, it's going to be 6. If it's 2, it's going to be 10. If it's 3, it's going to be 14. 4n plus 2. If you don't want to remember the numbers, most of the time the 2, the 6, the 10 are the ones we'll be using most commonly. Okay, so it has to have the right number of electrons. Okay, so it must be a ring. It must have p orbitals on every atom in the ring. It must be planar, and it must have the right number of electrons. Okay, so let's look at benzene. It's planar. It's a ring. It has 1 p orbital on each of the 6 carbons. Okay, and they are continuously forming around there. So we have 6 p orbitals, and each of those p orbitals has 1 electron in it. Therefore, we have 6 pi electrons. We follow all 4 rules: right number of electrons, the ring, the planarity, and having a p orbital. Okay, so every aromatic compound must follow these 4 rules. If it doesn't follow these 4 rules, it is not an aromatic compound. Okay, what time is it? Okay, all right. So, but it's not just restricted to carbon. We can actually have anything that can make an sp2 hybridized atom can be an aromatic compound. So we have a new class of compounds called heterocyclic compounds. Heterocyclic compounds are cycles that contain something other than carbon. Sulfur, oxygen, nitrogen, any of those can make a heterocyclic compound. However, if all the atoms in the ring follow those 4 rules of aromaticity, ring, p orbital, planar, and the right number of electrons, we now have heterocyclic aromatic compounds. So it's got something other than carbon in it, but it's still aromatic because it follows all the rules. And 2 of the most common ones are pyridine and pyrimidine right here. So let's look at that, okay? Does it follow the rules? Well, it's a ring, and we have a p orbital here for this double bond, a p orbital for this double bond, a p orbital, p orbital, p orbital, and oh, look, there's a p orbital on that nitrogen too. So we have 6 p orbitals, right? How many electrons do we have? Well, each of these double bonds is 2 electrons, so 2, 2, and 2, giving us 6 pi electrons. It follows all 4 rules. That means pyridine is an aromatic compound, but it's an aromatic compound with something other than carbon. So it's a hetero, meaning different than carbon, cyclic compound. Okay. In this case, we have 2 nitrogens that do the exact same thing, but it follows all 4 rules. Okay, so we've introduced a new kind of compound we haven't had before, that heterocyclic compound, and we have a new kind of compound in the heterocyclic aromatic compound. Okay, so let's prove to ourselves that pyridine really does follow the rules. First and foremost, the nitrogen in the pyridine atom must be sp2 hybridized, because we must have a free p orbital to be shared among the ring, okay? When we do that, notice that we have an sp2, we have a sigma bond over here, a sigma bond over here. That means this lone pair must be sp2 hybridized, okay? Each sigma bond is sp2 hybridized, and that lone pair is sp2 hybridized, leaving us our pi, our p orbital, to be our pi bonding, okay? Now, when we look at this, we have 1, 2, 3, 4, 5, 6 electrons. So it follows the rule of 6. It's a ring, it's flat, it has p's. It follows all the rules. However, when we look at the resonance energy of pyridine, it's only 134 kilojoules per mole, okay? Remember, benzene was 151. So it's not quite as stable as benzene, probably because of that nitrogen, but it still has that resonance stability. It still is more stable than isolated single and double bonds.
I have a question. Is there an example that you can think of that it might look like it's aromatic, but it's not? It's like it's almost like trying to trick you to look aromatic. Does that make sense?
Yeah, I have a classic example of that. And let's see, I guess there's enough room here. So what if we had this compound here, And then this was sp hybridized, but it had a positive charge here, which means it has an empty p orbital. Okay, so now we have a p orbital on every single atom right here. It's flat, it's planar. Each thing has a p orbital on it. Okay, the rule that breaks is the fact that it only has 4 pi electrons. 1, 2, 3, 4. So it looks like it could be aromatic, but the fact that it has the wrong number of electrons means it's not aromatic. But what if we took away that positive charge and added a negative charge and put 2 electrons in that p orbital? How many electrons do we have now? We have 6 electrons, which means when we have this negatively charged cyclopentadiene, it is aromatic. When it's not charged and has a hydrogen on it, it's not aromatic because it has one of the carbons is sp3 hybridized. When it's a cation, it's not aromatic because it doesn't have the right number of electrons. Does that make sense?
Yeah, that helps, because when I was first like just listening to all this, I thought it seemed pretty obvious, but I thought there had to be a trick somewhere where it's not always that obvious. So
Yeah.
this makes sense. Yeah.
You got to count usually it's where the electrons end up. You usually can figure out by hybridization whether you have a p orbital available. You can usually pick out a ring fairly quickly. However, once rings get too big, like 8 long, they start twisting out of plane. So you have to say, can it be flat and stay flat? Because when they start twisting out of plane or have a big group on it to make them twist, then they're no longer flat. So that's the other thing to look for. Usually it's number of electrons and whether it really is flat or not. Okay, so in this case here, we have our sp2 hybridized orbital has that lone pair in it, leaving 1 electron in our p orbital, and we have a fully aromatic system. Okay, so can we do that with 6-membered rings or 4-membered rings or 8-membered rings? Yes, we can. We just have to make sure we still follow the same rules. The first example of this is what we're going to call furan. So in this one right here, if I drew it differently, it would look like this. Okay, so that's that same structure. It's just drawn with the double bonds there. However, I didn't draw in the lone pair. So let me draw in the lone pairs. Okay. So if the oxygen were sp3 hybridized, it would not be aromatic, okay, because this would not have an available p orbital. However, because having that resonance energy is saving you energy, it's going to take that oxygen from that sp3 hybridized orbital with all of them equal and put those 2 electrons in a p orbital instead. Now, let's see if it follows the rules. We have a p orbital on every atom in our ring. We have a continuous set of p orbitals. It's flat, it's in a ring, and we have 1, 2, 3, 4, 5, 6 electrons. It meets all 4 rules. But to do so, that oxygen must be in that sp2 hybridized orbital, and that puts those electrons in that pi orbital sticking out in the same plane as the ring. Can we do that with nitrogen? Well, I think we can. Let's do it with nitrogen here. Now remember, nitrogen only has 1 lone pair, right? So in the case of the structure where we have nitrogen here, we have to draw it as sp2 hybridized, which means we have a p orbital. That p orbital is where those 2, that lone pair for the nitrogen is. So we have a ring, we have a continuous overlap of pi orbitals, and we have 1, 2, 3, 4, 5, 6 electrons, meaning it meets all of the rules. But notice we also, instead of having a lone pair sticking out here, it had to have that 3rd bond. And that 3rd bond is to hydrogen here. So that makes that hydrogen in the plane with the rest of the ring. Okay, so it doesn't have to be carbon, but it must be sp2 hybridized. Okay, So there's a wide variety of different compounds that have this aromatic structure. And remember, it's aromatic because it's saving energy, right? Nature is lazy. The more energy you can save, the more it will. And so we have a wide variety of these things in all the different parts of our body, including serotonin, indoles used in DNA building. These are used in as nucleic acid bases in DNA. So we're looking at a lot of these compounds exist, and a lot of them have nitrogens or oxygens or even sulfurs in them. And if you take the follow-on biochemistry course, you're going to learn a lot more about these. Okay, so how do we name these? Well, because benzene reacts differently, because benzene does not react like our other hydrocarbons, it has its own naming system. Okay, so these are new names you'll have to learn, and these names are also prioritized on that table that's in Canvas that has all the naming structures there. Okay, so on the last column, it tells you what you would name that compound if it had that functional group on it. So look for that on that thing. So because we have, it's not tricyclohexatriene, because it doesn't react like cyclohexatriene, so it has its own name. We call it benzene, okay? And so it's a nice liquid at room temperature. And benzene is going to be used as the primary on it. And so if we had this, we could name it ethylbenzene, or this would be methylbenzene, but it has a special name. The special name is toluene. Okay? So if I'm going to box it up, you'll need to know the name here. So this is pretty easy to figure out. The IUPAC name for this right here would actually be phenylethane, because the phenyl group acts as a substituent, and you have the longest parent chain is your 2 carbons. So boxed is something you'll need to learn. So we have benzene, we have toluene, that's just a methyl group on there. If we have a vinyl group or a double bond in conjugation with that styrene, well, bonded right next to it, right here, it's called styrene. And that name may sound familiar because those foam coolers are made from polystyrene. So you take a whole bunch of styrene molecules and put them together, and you end up with polystyrene. So that's that name there, styrene. And again, it's a sigma bond to a double bond between 2 carbons. Okay. So that's styrene. So kind of like when we had alcohols, they changed the names. We have an alcohol on a phenyl group or a benzene group, and so we call it phenol. So kind of like we're naming an alcohol, it's phenol. So that's boxed there. If we have a nitrogen on it, we call it aniline. Okay, think of amine, or aniline is the amine derivative of benzene. Now, once you have an aldehyde on here, it's just benzaldehyde. Carboxylic acid, benzoic acid. Okay, so the last one, I think in the special names category, is with a methyl ether attached to it. Okay, with a methyl ether attached to it, it's called anisole. Anisole. And they all change properties depending on how well they can hydrogen bond, or how well they react with other things. But again, they don't react like other alkenes. Okay. So we're going to go through in the next chapter, I believe, and talk about all the different reactions benzenes do. But right now, we're just going to talk about the different names and some of the other stuff. Okay, where are we? Yeah. Okay, so when we're naming things, if it just has a hydrogen on it, we name it as benzene. Okay. However, if it's attached to a hydrocarbon chain, it's now a substituent. Okay, and we call it the phenyl group. Okay, think of it as the phenyl, the benzene are their equivalent, but it's a phenyl group when it's attached to a hydrocarbon chain. So when we name this, we have 1, 2, 3, 4 carbons, so that's going to give us butene right here, but we have to locate the phenyl group on there. And so our phenyl group is on, well, we're going to number it from the one side or the other, so it's going to be 2 phenyl, 2 butene. And when we do our prioritization, the phenyl group is higher priority than the methyl group, The methyl group is higher priority than the hydrogen. Therefore, they're on the same side. It's going to be Z dash 2-phenyl dash 2-phenyl dash 2-butene. Okay. So whenever you have a long hydrocarbon chain, you are going to name it for the hydrocarbon with the phenyl group as an attachment. Same thing here. We have 2-carbon chain with an alcohol on here. The alcohol is a higher priority group, so it's named for that. And so we have 2-phenyl ethanol. Okay. We don't do it for methyl. It has a special name of toluene. But if we take one of these hydrogens off and attach that to something, it is now called the benzyl group. Okay. This is the phenyl group. Notice this is bonded directly to whatever you're bonding it to. This has a CH2 plus the benzene ring. That's the benzyl group. Okay. So in this case here, that benzyl group only has the chloride added to it. So it's benzyl chloride. So these are 2 substituent names you need to remember. Okay. The phenyl group is just the benzene ring attached to a chain. The benzyl group is the benzene plus a CH2 attached to something else. Okay. All right, so now that's how you name things if they have one thing attached to them. But when you have 2 things attached to it, you have a slightly different naming structure here. Okay, so the first thing is, if we start numbering around the benzene ring, and I'm just doing a raw circle here, and we have a substituent at one point, we're going to start with one of the substituents being our 1 position, and then we have opportunities to put things on the 2-carbon right here. So whatever naming our substance is on our 1-carbon, and then if the first substituent's on the 2-carbon, we call that the 1,2 derivative, or it has a special name. It's called ortho. Okay, they're 2 next to each other. It's ortho. Now, if instead of being on the 1,2, you attach it to the 1,2,3, that's called meta. Okay, so 1,2 is ortho. 1,3 is meta. And when it's 1,4, they're opposite each other. 1, 2, 3, 4. We call that para. Okay, so you can use the number or the abbreviation for ortho, meta, para. Ortho is going to be an O, meta is going to be an M, and para is going to be a P. Okay, so when we're naming these things, we look for the thing that has a special name. So in this case here, we have toluene right here because of that methyl group. We have a bromine attached in the 4 position, so that's 4-bromotoluene, or para-bromotoluene. I've been listening to a song called Dichlorobenzene, and it makes sense now. Yes, this is where it comes from, I guess. That's got to be 21 Pilots, right? Yeah. So anyway, in this case here, we have an amine on there. So we're naming it for that amine, and it's called aniline. And it's 3 positions over, so it's going to be 3-chloro-aniline or metachloroaniline. Okay. Now, if we have 2 methyl groups, we actually have a special name for that. 2 methyl groups is called xylene. But if you didn't want to do that, you could actually do it 1,3-dimethylbenzene or meta-xylene. So xylene is when you have 2 of these on there at the same time. So it's not toluene because you have 2 of them, so it's xylene. Okay. And then, of course, if you have name substituents and neither one is changing the name, you have to put the substituents in alphabetical order. Okay, so in this case here, chloro comes before the ethyl group here. So we have 1-chloro. The chlorine starts 1, 2, 3, 4, putting the ethyl group on the 4 position, ethyl, and then you have to name it benzene. So when it doesn't change the name, you put them all in alphabetical order and put the word benzene at the end. You could shorten that by just calling it para-chloroethylbenzene, because the para is telling you that they're in the 1 and 4 positions. Okay, Ortho is 1, 2, meta is 1, 3, para is 1, 4. Questions on that? All right, let's continue naming. If there's 3 or more substituents on there, you start with the thing that gives it the special name first, if at all possible, okay? And then you number it from the lowest, you try to get the lowest number possible. If none of them change the name, none of them are toluene or methanol, phenol or aniline, you just name them in alphabetical order, okay? So in this case here, the methyl group changes it to toluene. So because it changed the name, that's where you start with number 1. But then you want to number it such that you get the lowest number possible. And in this case, it's going clockwise, gives us a 2 and a 4. The other direction would have given us a 4 and a 6. So we're going to try to get the lowest number possible, like the way we usually do. So what we end up with is 4 chloro, 2 nitro, toluene. Okay. Now notice the substituents are in alphabetical order. Okay. So we identify it with the location by number, alphabetical order, and then what you named it for. Toluene because it has the methyl group. So the next one, because it has that OH on there, we're going to name it for that. And that OH on a phenyl ring is phenol. Okay. So I sometimes call them benzene rings, phenyl rings. That's where you get the phenol from, the phenyl alcohol phenol. Okay. And then this is easy because no matter which way you number, you're going to get the 2, 4, 6. And we have 3 bromines to give us 2,4,6-tribromo phenol. Now this last example, none of them change the names. None of them are special, right? So what we're going to do is we're going to do the lowest number possible. Previously, we did the one that was, the chlorine was the lowest alphabetical, and so we started there. But if we started with the bromine here, we're actually going to end up with a 3, 6 or a 2, 5, and that's going to be a higher number than if we started with the ethyl group. So we're still going to use the ethyl group, the lowest number first, and then alphabetization second. So in the case here, when we have the 1, 2, 4, that's our lowest number set possible. And so we have bromines before ethyl, this is before nitro. So we have 2 bromo, 1 ethyl, 4 nitro, and then benzene at the end. Okay, so we're just adding a little bit of special, a couple new rules to our benzene rings. We have names for special ones, and we try to go around the ring. We name it for what we can. If we can't, we use our traditional rules of lowest number and alphabetical order. Okay, questions on that? Okay. All right, take a break. We got the last 20 minutes in this thing, and then your guys are off to spring break or work or something. Okay.
Sorry, I do have a question.
Okay.
For the one that we just did, so do we start naming on where like the benzene would have started? Does that make sense?
Okay, so if you have one of those special groups like a phenol or an aniline or a toluene, you start, okay? So like this one, the methyl group changed the name from benzene to toluene. So that's where you start your number. If you don't have something that changes your name, you end up with benzene at the end. You get the lowest number for the groups possible. It's just like a long chain. You try to go whichever direction gives you the lowest set of numbers. And so it's the same rule. And then you just put them in alphabetical order after getting the lowest numbers.
Okay, that makes sense. Thank you.
Can we go back over the 4-chloro-2-nitrotoluene, please?
Toluene, yeah, okay. So the first thing we look for is it one of those special groups? If it has a methyl group, it's a toluene. If it has an amine on it, it's aniline. If it has an OH on it, it's the phenol. If it has an OME on it, that's anisole, okay? So if it's changing the name, you start numbering that direction first. You start from that number first, okay? So in this first one, we have a methyl group here, which is changing the name to toluene. So that's number 1. Now, we're going to number it so we get the lowest number possible. So if we numbered it in that direction, we'd end up with 4 and 6. So we're not going to number it in that direction, okay? It's usually fairly easy to tell. You just find your first group and then you number from that direction over. So we are going to number from this direction. So one's on a 2 position and one's on a 4 position, okay? So we have 2 substituents. We have located them properly because we've changed the name with this methyl group here. So now we just have to order them alphabetically. Chlorine comes before nitro. And now we have to put their numbers on it. 4-chloro-2-nitrotoluene. Okay?
Yes, thank you.
And do I have it? So yeah. So we need to know these ones that I boxed in here as the special names for benzenes. Flashcards or whatever it takes to memorize those. Okay. So we also have polynuclear aromatic compounds. What I mean by that is multiple rings fused together. Okay. Now we saw before that when we do these multiple fused rings together, we still have that saving of energy. They still have an aromatic nature to them, that resonance stability in them, but they kind of have different names. When we have just benzene by itself, right there, it's benzene. And then when we fuse, if we took 2 benzenes and put them with a sigma bond between it, that's just dibenzene or biphenyl, okay? However, if we fuse them together, that changes the name to naphthalene, okay? Now, if we fuse 3 of them together in a straight line, that's called anthracene. If we fuse 3 of them together in a non-straight line, it's phenanthrene. And then if we have 4 of them, like let's take this part off right here, that one right there with 4 of them all fused together is called pyrene. And by adding another benzene ring onto that, it's called benzopyrene, because you're adding another benzene ring. So these are found a lot in as a byproduct from hydrocarbon, from gasoline production. You get to see anthracene and naphthalene a lot out of that. Naphthalene is what used to be called mothballs. It has an odd odor and it repels moths. Anthracene actually is a really cool fluorescent dye. It has a bright blue fluorescence when you hit it with UV light. And I believe all the phenanthrene doesn't fluoresce, but this one does as well. Okay, so one of the things about them is that they can be biologically active. And sometimes that's a good thing, and sometimes that's a bad thing. And it turns out that if they can be reacted with enzymes within the body to create these weird epoxy derivatives, they actually can be carcinogenic. The compound itself isn't carcinogenic. However, the body will react it with one of its enzymes to make it something that's carcinogenic. Now, in this case here, the core of it, pyrene, does not react, but the enzyme attacks this one at the end because it fits into some biological pocket, some enzymatic pocket that wanted to create an oxidized species, wanted to add oxygens to it. And so when it did that, it created a diol right here and an epoxy group. That epoxy group can bind to DNA. And when it does, it makes it not be able to, as the enzyme that goes and copies DNA and opens it and closes it, comes to that spot with the phenanthrene, with the pyrene on it, and it stops. It can't reproduce, or it can't alter that. And so it actually alters the DNA and it produces a cancer-causing mutation. Okay, so again, the compound itself is not, but what is metabolized is. So even though the compound itself is safe, once your body starts metabolizing it, it's definitely converts it into something that's not. Okay, so that's one thing you can do, and that's a very odd reaction, and it only happens, we don't have this kind of reaction without enzymes. So that kind of reaction we don't see a lot. But how do benzenes react? Well, we can do oxidations of alkyl groups attached to the side of the benzene ring. So for example, if you took benzene and an oxidizing agent like this chromium, this chromic acid, or this permanganate here, it will not oxidize the benzene ring. The benzene ring is impervious to these two things. Now, if we remember what we had when we had alkenes, if we had alkenes and chromic acid, you would oxidize it down to an alcohol or a ketone or something like that. You would oxidize an alkene. Benzene, that resonance stability means it no longer reacts like an alkene, and the benzene ring is not oxidized. However, all the alkyl groups next to it are. So in this case here, when we have chromic acid or permanganate here, the nitro group doesn't react, the chlorine doesn't react, but this methyl group on the benzene ring does. And when it does, it oxidizes it all the way down to the carboxylic acid or the carboxyl. So that's a cool reaction because benzene is so stabilized by its resonance stability, it doesn't react. However, all the alkyl groups on it, that could be an ethyl group, propyl group, or whatever, it'll still oxidize it down to carboxylic acid. So we can use that to our advantage by taking hydrocarbons that come out of the petrochemical stream and turn them into functionalized materials to make things like polymers. And we'll talk about polymers again in chapter 16. But the idea here is that this is xylene, because we have two methyl groups on the end here. This happens to be paraxylene. You can also call it 1,4-dimethylbenzene. When we oxidize it with a strong acid, the benzene stays intact, but we oxidize both of these down to carboxylic acids. So that gives us benzene dicarboxylic acid, and notice they're opposite each other, which means it makes it really easy to grow long chains of these things. In fact, this is used in a compound known PET, polyethylene terephthalate ester, which is what the PET means. Some people just call it PET. So it's polyethylene terephthalate. And that's where we take this compound here from a hydrocarbon, and then we take ethylene glycol or dihydroxyethane. The dihydroxyethane, or I guess it would be ethane diol, the 1,2-ethane diol can react together here and here to create long chains. And these are used in plastic bottles as well as fibers like polyester fibers. And those silver balloons have a thin film of polyethylene terephthalate and aluminum. And that is the polyethylene terephthalate film is called mylar. And the aluminum keeps the hydrogen, the helium in, and the plastic keeps the aluminum nice and rigid. Okay, so we'll learn more about the polyethylene terephthalate in chapter 16. All right, we got 10 more minutes. All right, let's talk about some reactions of benzene. Okay, like I said before, they figured out that aromatic compounds were different than other things because they reacted differently. Okay, so if we have an alkene, excuse me, and we add chlorine to it, it's going to add across the double bond. But that doesn't happen in benzene. We do substitution reactions instead. But the substitution reaction needs a catalyst. So in this case here, we're going to use ferric chloride as a catalyst. And instead of adding across the double bond like if it was an alkene, we're going to replace one of the hydrogens with a chlorine. And the other chlorine is going to end up adding to the hydrogen to produce HCl. Okay, so we're not doing addition reactions on benzene. All the reactions we're going to be doing, most of the reactions we'll be doing on benzene are substitution reactions. And most of the time, we're going to be substituting hydrogen for something else. Okay, so in this case, chlorine plus a catalyst creates chlorobenzene. Okay, we can also do that with a strong acid like nitric acid in the presence of sulfuric acid. You would think, oh, that acid, that would add across that double bond. It doesn't. It does a substitution reaction. And what we end up doing is creating a positive charge on nitrogen here, and we end up putting that nitro group on there, and we generate water. So we get nitrobenzene from that. Again, it's a substitution reaction, okay? Not an addition reaction. Okay? So if we have that substitution reaction, we're only limited by having things that have a positive charge so that we can do it. So we have a bunch of different options. We can put chlorine and bromine on by just adding that iron catalyst. We can put a nitro on just by adding sulfuric acid and nitric acid. In the absence of nitric acid, with just sulfuric acid, we can put a sulfonic acid group here. So it's like sulfuric acid, but it's bound to benzene. So now it's benzene sulfonic acid. But we can also make new carbon-carbon bonds, okay? If we have an alkyl halide, we can do an alkylation on the reaction using a catalyst. Right here, these catalysts for putting carbon-carbon bonds are different. Notice there, aluminum chloride, AlCl3, is the catalyst when we're making new carbon-carbon bonds. Okay. So we start with an alkyl halide. It substitutes one of the hydrogens, creating our new sigma bond between two carbons and some acid. Okay. But what we can also do is take an acyl halide, which is a halogen on next to a carbonyl, and that's even more reactive. But what it does is it creates a ketone, a phenyl ketone. Notice that we have the bond between the phenyl group and the carbonyl, and we have another R group here. We can get a phenyl ketone from the system. Notice we're always substituting hydrogen. We're never doing an addition. We're always substituting. So in the benzene reactions, we always have these substitution reactions. Okay. And the type of reaction we have is not like we did with alkyl halides, where that was nucleophilic substitutions. We actually have what we call electrophilic substitutions, okay? Meaning we're creating a positive charge, and the positive charge is doing the work, okay? So I'm going to review this again when we get back from spring break, but I want to get through it. Again, the reason we can think about that, we have to form that positive charge, is that we're going to displace hydrogen, and hydrogen is going to come off as hydrogen plus, okay? So when we want to think about the substitution reaction, we have to make some positively charged species that's going to attack the benzene, and it's going to kick out hydrogen plus as our leading group. Okay. So now, all of those reactions I just showed you, the nitration, the chlorination, the sulfonation, the alkylation, and the acylation, all go through this same reaction mechanism. We have one mechanism in this chapter, and it's the electrophilic aromatic substitution reaction. Okay. So the first thing we need to do is we need to have an electrophile, something that has a positive charge, and then we need to have our stepwise mechanism. Okay. So what's the first step in our mechanism? Well, the first step in our mechanism is generating whatever that positive charge is, okay? So that's where those catalysts come in, okay? That aluminum chloride and an iron chloride are used to create our positively charged species. Once we have that positively charged species, the lone pair on a benzene ring acts as our nucleophile and reaches out and uses that lone pair to create a new sigma bond with that electrophile. Okay, now this is the slow step because benzene is stabilized by resonance energy to be more stable when it's in that ring, when it's aromatized. Okay, so it doesn't like to do this reaction. But when it does that reaction, it can spread the positive charge that it creates around the ring until we kick out a hydrogen. So it's stabilized by the idea that the intermediate, it can move that positive charge around the ring until it kicks out the hydrogen. And when it kicks out the hydrogen, it re-aromatizes, okay? We go from having those two double bonds and a positive charge to taking away the electrons from the sigma bond to hydrogen and putting them back in the ring, bringing us back up to 6 electrons, re-aromatizing the ring and generating our proton. Okay, so our 3 steps are create a positively charged species, have one pair of one pi bond, make a new sigma bond with that positive charge, and stabilize the positive charge in the ring. Then kick out a hydrogen, kick out a positive charge by kicking out a positive charge hydrogen to re-aromatize our ring. Those are the only 3 steps on all of these reactions. Okay. So let's show you what that looks like with the chlorination and the bromination and why we need to use that catalyst. Okay. The chlorine-chlorine bond is a nonpolar bond. Neither side is plus, positive, or negative. Okay. So it won't react by itself. Okay. So we have to trick it into having a positively charged chlorine to act in the reaction. So what we do is we put it with ferric chloride, which acts as a Lewis acid. It's an electron deficient iron, and it can use one lone pair of the chlorines to create a new bond there. And we end up with this charged species. We get this positively charged chlorine and this negatively charged iron in this complex. Okay. Now notice this is reversible. Okay. And then it can rearrange to give a positively charged chlorine by itself, and this entire complex over here is now negatively charged. So this creates the chlorinium ion. Okay. It does not create that chlorinium ion except in the presence of this catalyst. But what does that tell us? We now have a positively charged chlorine. We now have an electrophile. So that's the first step in our reaction, creating that electrophile. We used a Lewis acid to generate it. Okay. Now, what happens next? Well, the next thing that happens is one of the lone pairs of the benzene ring reaches out to create our new sigma bond. And so the positive charge is transferred from the chlorine to this benzene ring. And of course, we have resonance possible. So that positive charge is going to move around the ring and keep moving around that ring until something comes to help tug off this hydrogen. Remember, the hydrogen just can't leave by itself as a positive charge. A base has to come and create a new bond to it to pull it away. Okay. So it's just going to keep going around that until something that's basic comes in contact with it. In this case, we have the iron complex with the 4 chlorines on it has a negative charge. It's our Lewis base. And what's going to happen is the electrons that were making this bond between that 4th chlorine and the iron are going to reach out and grab the hydrogen. The electrons that the hydrogen had are going to go back into aromatizing the ring to give us our re-aromatized ring. And we're going to generate HCl. And we've regenerated our catalyst. That's why we call it a catalyst, because we start with it, we create our positively charged electrophile, but we get it back in the end after the hydrogen and transfer it off the benzene ring. Okay? So we use those same 3 steps from our general thing. We create a positive charge. The positive charge reacts with the ring, giving us a positive charge on the ring, and then we re-aromatize by pulling off a hydrogen. Okay, so we're going to continue this on after our break here. We're right here at 12:20, so I'm going to go ahead and stop recording. And if you have questions, please stay behind and ask them. If you don't have questions, please have a safe holiday, wear a mask, come back to us safely, please.